Hi, welcome back to Statics 1. Today we're going to be talking about the method of sections, another method for analyzing structures, very similar to method of joints in that you're solving essentially by applying your equilibrium equations. And you should remember these in 2D, at least, there's three equations. You can always solve for three unknowns. And so for the method of joints, remember we isolated a joint, and then we could solve for the unknown forces exerted by the other members on that joint. And actually the method of sections, the method of joints, it's kind of one and the same. And so I'll explain to you what I mean by that. So if we had a truss, very simple truss, like this. Okay, if we were to apply method of joints, method of joints. Oops, let me put in our, imagine that we've already calculated the support reactions. And of course we do that by creating a free body diagram for the entire structure, applying our loads, and solving based on our equilibrium equations. So let's assume basically that these support reactions are known. And now we want to isolate a joint and solve for the moment. So what we know we did before is we could just, and we pick one usually where we have two unknowns, so to start at. So we might start over here, and I'm just going to essentially erase the connection here and the connection here. And what you see is that, and I'll do this in red, I'll put our forces in red. So we have these unresolved forces, which were, here's a force outward from the joint, which implies, of course, tension, because it means the member is pulling on the joint. And then on the other side, we'd have another unresolved force. And so what we've done is we've isolated it, and then you see we have two unknowns. We have three equations. Oh, we're not going to use the moments equation because in this case, all the points go through a single point. All the forces go through a single point. So we're not going to have any moments, but we can solve for the forces, this force and that force. So all we've done is we've drawn essentially, and that's where the word comes from. We draw a section through our truss, and then we solve this. And the interesting thing about this is if what we're doing is we're taking internal forces, these are essentially internal forces, and we're turning them into external forces. So if we could just magically substitute, cut this, like let's imagine we had a chainsaw, we actually cut through our truss, and in order to keep it standing, we'd have to apply whatever internal forces were exerted before by the members on these endpoints, which are now like open endpoints. So as long as we could do that, and then this one's actually would be in compression, as long as we can push upward here, and whatever, this one's probably in tension, pull this way, this whole side would still stand. It didn't know that this was removed. Okay, so that's what we're doing the method of sections. So let's say we do that, we turn these internal forces to external forces, and then we can solve for these as if the same way we do like our response reactions. Okay, so that's what it is. It's basically turning, we draw a section through our truss, and usually you only want to have, you don't want to create more than three unknowns because we only have three equations. And then we solve for those unknowns by drawing a free body diagram and solving as if they were like response reactions. Same method we previously used to evaluate these response reactions. All right, so let's look at an example from the textbook. And this is what it looks like. I don't know the example. It's example 5.5 from the textbook. We have a truss. It's actually the same geometry as this truss here. Actually, with this, the way they've drawn it, this one is actually going this way. So a little different, but otherwise the same. And this is here, and then this is like that. This is a force of 400 newtons here. apply it over here, and I'm going to put my, like that, and like that, and I'm going to tell you that this is 4 meters here. So these spans are each 4 meters. And this one's 4 meters. Oh, I didn't draw it exactly right. And the height of this thing is 3 meters. And anytime you see something like that, 3, 4, 5, light should go off in your head. Oh, these are 3, 4, 5 triangles. Unfortunately, I didn't draw them to scale, but the 3 side should be a little squatter than the 4 side. And then we're going to use, instead of using like sine and cosine, we can always use the ratios, 3/5 or 4/5 to get the x and y components. Again, this is going to have a hinge on this side and a roller here. And instead of drawing them, we'll turn this into a free body diagram. So this is going to be a force here because the hinge, it has 2 forces. Call this AX, AY. And why are we calling it AX and AY? Because this is joint A, this is joint B, joint C, joint D, joint E, and then for some reason, I'm going by the textbook, they use joint G. So there is no joint F in this one for not quite understandable reasons. Any case, so now we have AX and AY, and of course we're going to have a DY. And instead of solving for these, well, I will tell you that the first thing we're going to do when you have a method of sections typically is to solve for your response reactions. And rather than solving for them, I'm going to just give you the answers. You know how to solve for them. You just write these equations, and you have 3 unknowns. You have 3 equations. You have 1, 2, 3 unknowns. Okay, there's one more force like this, 1,200 newtons. And I'll tell you that, rather than calculate, I'm just going to tell you what the response reactions are. We have AX equal to negative 400 newtons. So what does that mean when it's negative? It means that, though I drew it this way, the actual force was going opposite of what I presupposed it to be. Let's go with AY first, equals 300 newtons upward, and then dy is actually going to be 900 newtons. And if you look at the problem, it kind of makes sense. So this 400 newtons is balancing that 400 newtons. That would have come from our sum of Fx. And our AY and dy, our upward forces, add up to 1,200 newtons, which is what our downward force is. So that makes sense. And the fact is that our dy is much greater than the AY, is due to the fact that our 1,200 newtons force is towards the right-hand side, closer to our D support. So this makes sense. I didn't solve it for you, but you should know how to do that already. All right, so let's say we want to evaluate the forces within the GE, GC, and BC members. And so what we can do is we can actually create a section. And so we can just basically break this thing here and then reconstitute it. But we can reconstitute just the left-hand side with our external, what were internal forces are now going to become external forces. And those external forces we're going to have to solve using our equilibrium equations. So I'm going to draw a new free body diagram. And I'm only going to show essentially like the left-hand side. I can use either the left-hand or the right-hand side. Okay, so what I'm going to do is I'm going to only redraw the free body diagram for the left-hand side, and I'll do it over here. What I'm putting here is the free body diagram for the left-hand side. So I'll write that here. FBD, free body diagram of the left-hand side. LAHS, left-hand side. All right? I'm sure that's very clarifying. So let's draw our free body diagram. Calculate the values. So it's more like that. So you see we have 3 meters up and 4 meters over. Yeah, that looks about right. So it's going to be like 3, 4, 5. So the slope is essentially 3/4, and that'll help us with solving this thing. So now we're going to have over here And what else do we have? So we have AX. So in fact, AX is pointing this way. It's 400 newtons. We have our AY, which is 300 newtons. Okay, so those I got before when we calculated our response reactions from the entire truss. And we're going to have, didn't mean to draw that one so long. And I'll do these in red so you'll understand that this is going kind of over that way. And we have one across here. So this is G. Then over here is going to be E. I'll just put E there just so we keep in mind that it's there. And over here we'll keep C. Just to remember that this is going to point to C. And this one also is pointing to C. And this is also a 3, 4, 5 triangle. And now we can draw our previously internal forces, draw them as external forces. And that is, what letter is that? We call that B. So let me write these all out. This is point A, B, okay, there's C. We already did that one. And here's my forces. So I have a force BC, and I'm drawing them, of course, as I always do, as if they were tensile. And then we know later, if you get a negative value, that tells you that, in fact, it was in compression. Here's my other one. So this is FBC, FBC, going from B to C. This one will be FGC, going from G to C. And this one here is going to be FGE, because it goes from G to E. Okay, so this structure will still stand as long as you impose what were previously the internal forces, apply them as external forces. And most likely from a truss, we haven't really talked about this. Most of the cases, if you have the loads at the sort of at the deck of your truss, typically you'll have tension at the bottom and compression on top. So we're going to expect FGE basically to be actually in compression. This will be in tension. This could be either, we'll wait and see. I think in fact this case is going to be in tension. But I'm not sure. Okay, so let's solve for this. How do we do it? We're going to use our equilibrium equations. And you got to think strategically how you do these. What I would do is solve for the moments about G first, and that will give you directly the value of FBC. So let's do that. Remembering that we have 3 meters vertically here. This is getting a little crowded. 4 meters horizontally here. So let's evaluate that. So the sum of the moments about G, about G equals 0. So both of these, no contribution. This one is going to have, this FBC is going to have a contribution with a moment arm of 3 meters. And this is going counterclockwise. So it's equal to FBC times 3 meters. Right, the moment arm is 3 meters in this case. And then we have all these other ones. Oh, we have 2 more. We have a force here and a force here. This force is 400 newtons in this direction, so that's going to be clockwise, so it's a negative value. 400 times 3. So negative 400 newtons times 3 meters. And then our last one is 300 newtons. This one is also, where are we? Our, here, moment about G, also clockwise. Yep, clockwise. So it's going to be 300 newtons minus 300 newtons times, in this case, it's going to be 4 meters, because we have 300 newtons times this length is going to be our perpendicular distance from the line of action of this force. We have this distance here. It's going to be 4 meters. If we'd solve this as a 1200, so we have negative 1200 minus negative 1200, it's negative 2400. And I'm running out of room, so I'm just going to do it in my head. We put it on the other side, we end up with 2400 Newton meters equals FBC times 3. And then we divide that by 3, and we end up with FBC equal to 800 newtons. Okay, so it's a positive value, so we know, we drew it as a positive value, so we know that it's in tension. So I can put here equals 800 newtons in tension. All right, so now so we use our moment equation. Let's use our y value. We're going to use next the sum of f of y equals 0, because we only have one unknown which has a y component. FGC has a portion of it. A y component of FGC is in the vertical direction. It would actually be 3 divided by 5 times FGC. That would be our y component. So I'm going to write here the sum of Fy equals 0. That's our equilibrium equation, right? Just like we always do it. And it's going to be equal to, and again, FGC is pointing downward, so it's a negative value. Negative FGC times 3 over 5. Right, because the ratio of this thing is 3 over 5 in the along the hypotenuse. That's the y component of FGC. And the only other y force is that one, 300 newtons. And that one is positive. 300 newtons positive. So if we look at this, we have 300 newtons. So what we're going to do is we're going to take the 300, put it on the other side. We have negative, but the negatives will cancel out. And then we multiply by 5/3. We end up with FGC equals 500 newtons. FGC equals 500 newtons. Positive value. So our initial presumption that this was in tension was correct. So this equals 500 newtons in tension. That's a T. What we do is we put T for tension and C for compression. So now let's solve for this one. So we have all of our forces. I don't want to do it down here because I won't be able to write down that far. I'm going to have to do it. I'm going to have to steal this space up here. All right, so we magically erase the board over here. Now we're going to write our sum of F in the x direction. So a summation, right, of F x equals 0. So what are all our forces in the x direction? We have this one here, negative 400 newtons. Negative 400 newtons. That was our support reaction. We have FGE. That's the last one that we're trying to solve for. I'll put that right here. Plus FGE. We have FBC, which we know to be 800 newtons, and that's acting in the to the right. 800 newtons. What else do we have? Oh, we have our FGC. So FGC is 500 in this direction. And since it's a 3, 4, 5 triangle with 4 in this direction, it's going to be 4/5 times our 500 newtons. That'll be to the right. So that'll be plus 4 over 5 times 500 newtons. Let's see if we got all of them. There's this one. That was our 400 newtons, negative. FGE, we have that. FBC, we have the 800 newtons. And FGC is this one, which is 500 times 4 over 5. That looks exactly right. And so let's see if we can evaluate this. So this is 400, 1200 minus 400. 1200 minus 400 is 800, and I'll put that on the left-hand side. We have negative 800 newtons equals FGE. So we've actually solved for FGE, which equals negative. This one here is, what is this doing? Oh, that's our letter. This is going to be equal to negative 800 newtons. We know if we've drawn it as in tension, the result comes out negative. In fact, this was in compression. So we've solved for this using the method of sections. Here's our solutions. There's one solution, 2, and 3. All right, so remember the method of sections. You draw, first you solve for the external support reactions. Draw a section through no more than 3 members, so you have 3 unknowns. And then you can solve for those internal forces as if they were external forces, because those external forces are what's needed to support this thing when you essentially rip the truss apart, because those forces still have to be there to hold the truss up. Okay, so that's what we did. So that's kind of the thought process behind this. You have to think strategically. Just remember of picking like where to evaluate the moment and which one to do in which order, because you want to be able to solve these. And you see how I did it, where I didn't actually have to substitute anything. I didn't have to actually solve any like simultaneous equations. I wrote them so that we had equation with just one unknown in each case, and then we could solve for them directly. All right, so that's the method of sections. Email me your questions, and otherwise I'll see you in class.